hello everyone. We are doing video, it's 1.D.2 mass spectroscopy. If you'll notice, there is no video on 1.D.1, and that's really sad. But we will cover that in class because it's more like a really boring history of atomic theory-ish thing. It's more of I will hand you the information because it's just easier that way than me standing here and writing a bunch of notes on the board and you staring at my bald spot because it makes me self-conscious. Okay, so 1.D.2 mass spectroscopy. Okay, so let me jump off to the side so you can write down the notes. There's going to be these notes and then a little bar graph that I'm going to butcher and try and put up freehand, and then we'll talk about it. Oh, so here I go. And I'm back. You like that? That's how I ran in PE. That's why people made fun of me. Alright, so isotopes. So we have atoms that have the same number of protons, so they have the exact same reactivity. They will have the exact same properties. However, they'll have different numbers of neutrons. This is called a pound sign. It means number. I'm not hashtagging my lectures. So anyway, atoms with the same number of protons but different number of neutrons. So they will have the exact same properties. Let's say isotopes of carbon. Different isotopes of carbon will have the identical properties of everything. So carbon-12 and carbon-13, those are their mass numbers, by the way. Carbon has a mass of 12, carbon-13 has a mass of 13. Carbon-12 and carbon-13 will react the same exact way. They'll do everything the same way. One just weighs a little bit more than the other. All right? So the way we figure this out, or the way we can figure out which one's which, is through something called a mass spectrometer. All right, a mass spectrometer is essentially, let me find a spot here to draw it. It's essentially a tube. All right, so what you're going to do, there you go. What you're going to do is it's a tube, and when you inject your sample in, it's going to make the sample charge. So it's going to pass it through a field, and it's going to charge your sample. So everything in your sample is going to have a charge. So let's say it's carbon. All right, let's say we want to know how much carbon is in a sample. We add the carbon, and it's going to charge the carbon. So your little carbon sample, everything will be an ion. And then we'll say we have a positive plate up here and a negative plate here. All right. So the ion has a charge. The top of the tube has a charge. The bottom of the tube has a charge. And what they're going to do is they're going to start shooting it down the tube. Okay? And what's going to happen is the heavier carbon is going to fall towards the charge plate first. Alright, so we'll call this carbon-14. The middleweight carbon is going to go a little bit further, but eventually it's going to succumb and it's going to fall towards the plate next. That's called carbon-13. And then you can see where this is going. The lightest carbon is going to go the furthest. This is carbon-12. Okay? It's a little more scientific than this. This is obviously a pretty simplified version. But anyway, the heavier carbon won't go as far, and the lighter carbon will go the farthest. So now we've separated out our carbon-12, our carbon-13, and our carbon-14. This is how they do carbon dating, by the way. So let's say you have a book, and you don't know how old that book is, but you know it's old, thousands of years potentially. What they'll do is they'll take a very small little cut of the vellum, because it's probably not paper, or papyrus, and they will vaporize it and they'll put it in this chamber. And they will charge that and they will send it shooting down this column. And based off of the different relative amounts, they can figure out how old that book is. Because carbon-14 degrades is a little less stable than carbon-12. So carbon-14 is going to break down at a very predictable rate. So if we know how much carbon-14 in the vellum has broken down, we know how old it is. Okay? It has to do with half-lives and things like that. And we'll talk about that all when we talk about half-lives. But so when they do something like, oh, we did carbon-14 dating, and we found this artifact to be 2,000 years old. That's how they did it. They vaporized a little piece of it, they charged it, they ionized it, and they sent it down this tube. And they compared the relative amounts of carbon-14 to carbon-12. Because carbon-14 disappears as it gets older. So if I have a lot of carbon-14, it's fairly young, and if I have almost no carbon-14, it's very, very old. So that's how they do it. One thing that we do, or rather that chemists have done, I never did it, and you'll never do it, they can separate the isotopes by mass. This is a mass spectrometer. That's what they do with mass spectroscopy. And then they use this isotope data to come up with the average atomic mass. So you'll notice carbon's average atomic mass is something like 12.0106. I'm looking at my periodic table. Oh, 0.7. Rookie mistake. Okay. Carbon should weigh a whole number, right? Because protons and neutrons both weigh 1. And so, why is that a decimal? It's a decimal because you have to take into account the different mixtures of carbon, okay? So they take a nice big sample of carbon, they find the relative amounts of each isotope, and that's why this is called the average atomic mass. They take that into account. So that's why almost all your mass on the periodic table are not whole numbers. Ones that are whole numbers, you'll notice, are your bigger elements, and they're in parentheses. Generally, that's because they're man-made. So if you have a man-made element, generally they only make one isotope of it, so it has a very exact atomic mass. Right? And then last but not least, let me show you what a mass spectrometer's readout will be. It's called a mass spectrum, but I started saying the wrong word, so I just had to go with it. It's a bar graph, so I'm going to make a bar graph. We'll say it's carbon. I am making all of these numbers up, by the way, so these are not the real mass spec for carbon, so don't go Google it and come and say I'm wrong, because I know these are not. This is an illustrative purpose. So you'll get a readout, a mass spectrum, and it will say 60% carbon 12, 30% carbon 13. It doesn't talk to you, by the way. I think I talked about this in a previous video. They don't talk to you. It would make it a lot cooler if they did, but they don't. But I am pretending they do because my life is boring, staying here after school, making a video, and I'm rambling. There we go. So this is a mass spectrum, okay? It tells you the relative amounts in that sample. So let's say it didn't give me the element. Let's say I plug in an unknown sample and I get this readout. And you're like, oh boy, what is this? And then the question could be, carbon has 3 naturally occurring isotopes. Nat-iso, that's how I'm going to abbreviate natural isotopes. And nitrogen has 2 naturally occurring isotopes. Which is probably the element dictated in the mass spec below. You'd be like, oh, clearly these are carbons because there's 3 naturally occurring isotopes. A nitrogen one would only have 2 bars. Okay? So not too bad, but you need to be aware of it because it is a very powerful tool in just dating different artifacts, as well as why are the masses on the periodic table not integers. It's kind of a big deal in chemistry. All right, cool. Have a great day, and I will see you tomorrow in class.